welcome to our first conversation on work and energy. Work and energy are two terms that you use in the English language fairly interchangeably, um, but in physics we have a pretty strict definition. We're going to start talking about work. So work is an ability to apply a force over a distance. And its units are joules. Well, I think I misspelled that. I think it's Joules, which we just give a capital J. So the formula we use is work is equal to F times D, the ability to apply a force over a distance. If we're looking at the joule, that means that joule is the units of work has to be equal to a Newton meter. Newtons we know, just as an aside, from F is equal to MA, means that a Newton is equal to a kilogram meter per second squared, which means that a joule, even farther broken down, kilogram meter per second squared times a meter, means that in the most basic units, a joule is a kilogram meter squared per second squared, would be kind of the base unit associated with a joule. There's a caveat here. It's not quite your normal three-variable equation where I can just give you two variables and you shove two of them in and then find out what the third one is. The force and displacement must be in the same direction. So, if we look at an example, and we'll start off with a super simple one, and we will just have a box that is pushed 7 meters with a, bring up some tools here. Let's just do a 3 Newton force. So notice how my displacement is parallel to my force, which means I can just do work is equal to F times D. Work is equal to force times displacement. My work is equal to 3 newtons times 7 meters. So my work is equal to 21 joules. But now what happens, we take a little bit more of a realistic example, and we have our object that's being pulled along the ground with a force of, let's do 3 newtons again, and let's do a displacement of 7 meters. But this time it's at an angle, and let's just call that angle 30 degrees for fun. So now what we're going to have to do, this is pretty common, is we're going to have to split it into components. So we're going to split it into components that are both parallel to this displacement and perpendicular to this displacement. So this would be our Fy, and this would be our Fx. We are concerned with the Fx because that's the one that's parallel to our displacement. So we're going to use cos of 30 is equal to my adjacent component over my hypotenuse. So my adjacent component is equal to F cos 30. And if we want to generalize this a little bit, which I can put in brackets, that means that work is going to be equal to F cos theta d, where theta is the angle between that displacement and the force. In this case, we had a work is equal to 3 cos 30 times my displacement, which is 7. I haven't pre-done any of the calculations this time, so I'm going to have to type it into my calculator. 3 times cos 30, close the bracket, times 7. So this amount of work is equal to 366, 18.1 joules. Notice how it's less than the previous example. So in reality, if both of these things happened, a 3 Newton force over 7 meters that's parallel, or a 3 Newton force at an angle, example 1 would have got the work done probably faster if they were identical scenarios. And some of that work is gone, in example 2, is just gone to lifting the object, which doesn't actually do any work at all. So we need to talk about, or we should talk about, a couple of conceptual examples. One of my favorites to talk about is usually in class. What I do is I get someone to hold both of their arms out straight, and then we give them a great big huge mass to hold on to, usually the overhead projector. It's about the only thing I use my overhead projector for right now. And I tell them to hold it with their arms out straight in front of them. So their arms are parallel to the ground. And I ask the person holding the overhead projector how much work they're doing. Usually, if this is a heavy enough weight, and I talk slowly enough, at this point in time they start to shake, and their arms start to bend because it's too heavy for them to hold out, and they feel like they're doing a ton of work. And this would be our normal English type definition of work, where they're doing something physical, they're doing a physical task, and they're like, yeah, I'm getting some work done. However, in the physics definition of work, since there is no displacement involved, that person is doing absolutely no work. We can also look at, and this one is quite similar, a waiter walking across a room holding a tray of food. Some velocity. Happy waiter walking across with a tray of food. And we can ask, how much work is that waiter doing on the tray of food? Well, if we were to draw a little free body diagram on this tray of food, they're walking at a constant velocity across the restaurant. The force they're applying is up, and it would be probably a normal force on it. This is the force that they are applying, so this is the work that the waiter is doing on that. And the displacement is perpendicular to the applied force. So conceptually, since we cannot break that applied force into components where any component would be parallel to the displacement, no work is done. We can also type this into the equation that we just derived, where work is equal to F cos theta times the displacement. Because if we look at this piece in the equation cos theta, which in this case would be cos of 90, you can go ahead and type it into your calculator, but I guarantee you that the cos of 90, what you're going to get if your calculator is in degrees, is 0. So both mathematically and conceptually, they're doing no work. So let's talk about energy. Energy is the ability to do work. And I think this one lines up pretty well with our English definition and what we think about energy in the real world. It doesn't necessarily mean that the thing is going to do work, but it could do work. So when we talk about and think about some of our energetic friends in a classroom, they could take all of that energy and put it into doing work. However, frequently some of our most energetic friends don't necessarily put all of that focus into doing something that we would consider constructive or work. We define energy talk about kinetic energy and gravitational potential energy. So kinetic energy is the energy of motion. So what this is saying is that an object in motion has the ability to do work. An object in motion can do work. So that means an object can apply a force over a distance. Let's write that down. Can apply a force over a distance. I find the easiest conceptual example of this one is to imagine one object that's moving and then run it into another object. And that means that that moving object will apply a force to the stationary object over a distance. You can think of a contact sport like rugby or football where we have one person who's moving with a velocity, give them some speed lines, into another person who's just standing still. Obviously, the person with a velocity is going to contact the person with no velocity, and eventually they're going to come to a stop. So the maximum amount of work, and that's also once they come to a stop, is when the force will stop being applied. So if we look at how much work this person could possibly do, work, which is equal to force times displacement, the whole time he's applying a force, he would be accelerated, and we know that F is equal to ma. So we can go ahead and we can substitute that into this equation, and this is a little derivation that will give us an equation for kinetic energy at the end. Work is equal to mass times acceleration times the displacement. And if we want to know what that acceleration would be, given when we talk about displacement and this initial velocity, we can use the kinematics equation, Vf squared is equal to V naught squared plus 2AD. When he's done the maximum amount of work, his final velocity will have gone to 0. So we end up, if we rearrange this, a negative V naught squared over 2D would be equal to A, and the negative just indicates a direction in relation to that acceleration, and work, it turns out, is actually a scalar, not a vector, so we don't care about derivation, so I am going to ignore that negative sign as I take this expression and substitute it in for my acceleration. So my work is equal to m v naught squared over 2d is 2d is my acceleration times d. We notice how my displacement cancels. This is independent of the distance he applies the force over, but the amount of work he could do is dependent on just his mass and his velocity. This is the definition of kinetic energy. So the kinetic energy is equal to 1/2 mv squared. When we talk about energy, we can give it a symbol capital E, and then to give it the type of energy, we give it a lower subscript like this. So this is kinetic energy is equal to 1/2 mv squared. And that's how much work an object could do if it's moving with mass. We can do a similar derivation for gravitational potential energy. So gravitational potential energy, let's talk about potential energy first. Potential energy is energy stored in a system of objects. So when we talk about gravitational potential energy, what we're usually talking about is the Earth and an object. So if you have an object that is some height above the Earth, and we could allow this object to apply a force on things. So we're going to do another quick little derivation. Work is equal to force times displacement. The maximum force that this object could apply to another object due to gravity, because we're talking about gravitational potential energy, would be the force due to gravity over that displacement. So the maximum force would be mg, and the total displacement it could possibly apply that over is the height. So this is potential energy. EP is equal to mgh. That one's a little bit faster, a little bit simpler. I don't think they're incredibly complicated to take those, and I could give you the potential energy and mass and the acceleration due to gravity, and you can find out how high it is, or vice versa. I think you guys are all at the point now where if I'm just giving you variables and you're plugging them in, that's a completely comfortable thing to do. But what I would like to now do is look at a second way to calculate work. And that is work is equal to change in energy. So this delta symbol always means final minus initial. So this is E final minus E initial. So now we have three ways to calculate work. We have work is equal to force times displacement, and we have work in a change in energy. And I know what you're going to say. You're going to say, Mr. Collins, it's only two ways. We just said two ways. But we have two different types of energy. So we could do work is equal to change in kinetic energy, or we could do work is equal to change in potential energy, or we could do the first one, which is work is equal to force times distance. We usually just write these two together as work is equal to change in energy. In reality, we could change something's energy both with gravitational potential energy and kinetic energy, but in Physics 11, we usually only change one of those two things. Let's look at an example. I can't remember what example number we're on, so let's just call it A. Example A. How much work is done lifting an object from 3 meters to 7 meters, and I should probably give this object a mass, let's give it a 2 kilogram mass. How much work is done lifting an object from 3 meters to 7 meters? So when we're lifting something, what we're changing is its potential energy. It's going from one height to another height. So what I would do is I would choose to calculate work as work is equal to change in potential energy. If we're given a force, I would use work is equal to force times displacement. If we're changing the height of something, we're changing its potential energy, so I would use work is equal to change of potential energy. If we're changing something's velocity, then I would use work is equal to change in kinetic energy. So work is equal to change in potential energy. Work is equal to work is equal to EP final minus EP initial. So my work is equal to mgh final minus mgh initial. Notice how neither my mass nor the acceleration due to gravity change over that time, so I don't need subscripts on them. Notice how m and g are in both terms, so I can actually factor it out if I wanted. H final minus h initial. So my work is equal to m2 times 9.8 times my final height, which is 7, minus initial height, which is 3. 2 times 9.8 times 7 minus 3, and I get 78.4. My work is equal to 78.4 joules. I can do a similar example where we talk about, I think it's example B. How much work is done? Accelerating a car, let's say it's 1,000 kilograms, from 2 meters per second to, I don't know, 17 meters per second. So we're changing something's velocity. I want to think about change in kinetic energy. I've changed how fast it's moving. Work is equal to delta EK. Work is equal to EK final minus EK initial. My work is equal to a half mv naught, or v final squared minus a half m v initial squared. Notice how a half m is in both terms. Makes it a little bit easier to plug it into my calculator, but you could have done it in the line above if you want. My work is equal to a half 1,000 17 squared minus 2 squared. I grab my calculator again. A half times 1,000 times 17 squared minus 2 squared is equal to 142,500, or to 3 sig figs, 142,000 joules of energy.
Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. And that goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment, or leave a comment on the YouTube video. And step number three to success is look after yourself. Eat good food, get some exercise every day, and socialize as much as you can right now. I hope you guys are all doing well, and I will talk to you soon.